In this video, we will be learning about how to perform three-dimensional rotation in general. So in the last video of mine, we have seen how to perform rotation around principal axes, right? So say if I have an object, how to rotate it around either x-axis or y-axis or z-axis. Now, what if I want to rotate it around some arbitrary axis like this in my coordinate system? So that is what we are going to see, and we are going to split up this rotation into two cases. The first case is rotation in 3D when the axis of rotation is parallel to one of the coordinate axes. The other case is when the axis of reference is not parallel to the coordinate axis. Apart from these two rotations, we'll also be looking at 3D reflection and 3D shear. So taking our first case, now let us say I have an axis like this as my reference axis. I want to rotate this tetrahedron around this axis. In this case, how to go about it? So I know how to rotate it around x-axis. Now I want to rotate this object around this axis that is parallel to my x-axis. So what I can do is I can translate this object such a way that this reference axis comes and sits on the x-axis. Then I perform my rotation around x-axis. That is, I apply matrix Rx of theta. That would rotate my tetrahedron like this by theta degree, and then I translate it back to its original position. So if I place my axis back to its original position, then I would get my rotated object like this, which will be rotated around this reference axis for me. Now, so these are the steps that are involved. We translate the object so that the rotation axis coincides with the parallel coordinate axis, and then we perform rotation around the principal axis on which the rotation axis is aligned with, and then we translate the object back such a way that rotation axis is moved back to its original position. Now that we can do by applying translation and then by applying Rx of theta and then inverse the translation on an object. Now if I perform this, what it gives is this result, right? So these steps are pretty straightforward. We know this matrix, we know translation matrix, we know how to inverse a translation, and multiplying all this, the resulted matrix, if we multiply with the object, what we get is rotation around the axis if it is parallel with one of the coordinate axes. Now the same goes if the reference axis is parallel to y-axis or z-axis. What changes is what rotation matrix I apply, either x-axis, y-axis or z-axis, based on to which axis the reference axis is parallel with. The next problem that we would be looking at is this. What if I want to rotate my object that is not parallel to any of the coordinate axes? That is something like this. Now say I have an axis like this. I want to rotate this object around this axis. In this case, how to go about it? So what I know is how to rotate around x-axis, y-axis and z-axis, and we already discussed this is a case where this axis is not parallel to any of these axes, so that we can just translate it and apply rotation as we have seen in the earlier case. We cannot go with those steps. So what to do? In order to do that, what we can do is, the very first thing is take two reference points along this axis, let us say P1 and P2, and then translate this axis such a way that it comes and sits on the origin. So translation. Let us say the P1 is defined with x1, y1 and z1, P2 is defined with x2, y2 and z2. Then we apply translation where the tx and ty and tz will be minus t1, x1 and minus y1 and minus z1. So based on what the coordinate position is with respect to the point which should come and sit on the origin, we calculate the translation matrix. Now once we translate it, the axis will come and sit like this, aligned onto the origin. Once that happens, we have to rotate this axis such a way that it should come and align itself with one of the principal axes. In this case, it is aligned with z-axis. Now the next step is to apply rz of theta. So since this axis is aligned with z-axis, we apply rotation around z-axis. Once it is rotated around z-axis, we rotate the object, the axis back such a way that it goes back to its original orientation, to this step, right? So once this happens, so let us say I have applied a step called as R here, then I'm supposed to perform R inverse here. That's the idea. Now once this happens, now don't wonder what is R. We would be discussing this. R is actually a combination of multiple rotations. We would be discussing this in a couple of minutes. So once I perform this inverse transformation, then it would come back, this axis would come back to its original orientation. After this, I'll have to move it back to its original position. To do that, what I have to do is I have to inverse the translation that I would have performed here. So if I inverse it, my axis will go and sit to its original position. Now say I have an object here that would come and sit over here with respect to that axis, and then if I rotate it, after rotation somewhere, if the object is over here, right, after rotation probably I would get it somewhere here, and then if I move back it would come here, and then if I move it back I would get the object here. So that's just an idea of how this rotation is performed with respect to a arbitrary axis. Now we'll see the steps one by one. So these are the steps that are involved. So the same steps is given in terms of points. So you guys can refer to those points by pausing the video. Anyway, I'm going ahead as I have already explained it. Now the very first step that I'm going to do here is I would take a point called P1, which is x1, y1, which would be defined as x1, y1, x1, y2, y1, z1, and I would take another point along this axis called as P2, and that would be defined as point x2, y2, z2. Now if I subtract this point with this point, then what would I get is a vector along this axis. Now once I have this vector, I will have to convert it into a unit vector. Let us call this unit vector as u. So I can convert by dividing this vector with its magnitude. So what I have, the result at the unit vector, let me call it as a, b, c, where my a is x2 minus x1 divided by magnitude of v. Similarly, b is y2 minus y1 divided by magnitude of v, and c is z2 minus z1 divided by magnitude of v. Now what we would have after this step is a unit vector along this axis. Now once I have my u, which is defined, since it is a vector, I can reposition it in my coordinate system. It should not make any difference. Now I can bring my axis back to move my axis to the origin by translating it by minus x1, minus y1 and minus z1. All the points along this axis is translated by minus x1, y1 and z1. That makes our p1 to come and sit at origin, which we shall call as p1 dash. So this is the translation matrix that I would apply to perform this translation. Now once this happens, our next step would be to rotate this axis such a way that it comes and sits on Z axis, right? Now to do that, I might need this angle between the axis orientations, the original orientation and the Z axis. So let me call this angle as some phi. First challenge is I don't know what is my phi. Second challenge, if at all I know my phi, I will have to apply a rotation matrix which rotates this axis such a way that it comes and sits on my Z axis. But to perform that, I will have to know the matrix to rotate around this axis, right? So if I swing this axis such a way, with phi in this direction, then it would be equivalent to rotating around this axis, right? And I don't know the matrix to rotate around this axis. What I know is the rotation matrix for rotation around x-axis, y-axis and z-axis. And of course, this is one such arbitrary axis for around which I'll have to rotate, which is exactly the problem what we are trying to address here. We are trying to perform rotation around an arbitrary axis. So if I have to perform this step as a straightforward step, then the visible solution for us is this, which is quite straightforward. But why I can't do this is I don't know how to rotate around this arbitrary axis. That's exactly the problem we are going to solve here. So this is not a feasible solution for us. Instead, what I can do is I can actually I know how to perform my rotation around x-axis, and I know how to perform rotation around y-axis and around z-axis, right? So I can combine these rotations in some order, and I should be able to rotate this axis on the z-axis, right? Now how to do that? In order to do that, what we will be doing is, first thing, we rotate this axis such a way that it comes and sits, or it comes and falls on xz plane, something like this, right? For that, let us say the angle that this axis is making with xz plane is alpha. Now if I'll have to rotate this, if I have to perform this, let us say I know my alpha. In case I know my alpha, then all I have to do is apply Rx of alpha to perform this rotation. Because this is rotation around x-axis, so I'll have to rotate my object in this direction around x-axis such a way that it will come and sit on my x and z plane. Now I know this matrix. What I don't know is what is alpha. We will see how to find this alpha. We don't even have to know about this alpha as far as we are able to build the matrix Rx of alpha that produces. If we are able to build that matrix without even knowing alpha, then we are good to go with that rotation, right? So we'll have to rotate this by alpha. Now once I rotate this by alpha, what I get is this axis gets rotated like this, which will be on my xz plane. And then let us say this axis is making, this rotated axis is making some angle of beta with z axis. It's already in xz plane, so once it is on xz plane, it is making beta degree with respect to z axis. To perform this rotation, I'll have to rotate this axis by beta degree to align this axis on z axis like this, right? Now, around which axis am I supposed to rotate this axis in order to bring it on z axis? That is in around y axis. Meaning to say, I'll have to apply Ry of beta. So if I perform y-axis rotation with beta degree, then this axis which is in which we brought onto xz plane will be rotated such that it would be aligned with z-axis. Now, to find out our alpha and beta, we don't know what is our alpha and beta, but as far as if we are able to find out cos alpha and sin alpha and cos beta and sin beta, which are actually the components of Rx of alpha rotation matrix and Ry of beta rotation matrix, it should not be a problem for us if we don't know alpha and beta, right? As far as we get cos alpha and sin alpha and cos beta and sin beta, finding out what is alpha and finding out what is beta should not be a problem for us. Now, how to go about it? So this is what we are talking about. So we had a unit matrix which is U, which was this, right? So we have that unit matrix at the origin. Now if first thing what I have to do is I have to perform rotation by alpha degree around x-axis to bring this vector on xz plane, and then I'll have to rotate this by beta degree to bring my vector which is in xz plane onto z-axis. So this is combination of two rotations. So basically what we mean here is to bring this axis from its original orientation to z-axis orientation, we will have to first bring it onto xz plane and then rotate it around y-axis. So that is a combination of two rotations. That is exactly the reason I use the notation R, and here I use the notation R inverse. Nothing else. It is combination of two rotations. Now how to find out alpha and beta? It's okay for me to not know my cos alpha if I am able to get my cos alpha and sin alpha. Not being able to find out what is my alpha shouldn't be a problem, because this is what we are concerned about. These are our components in the rotation matrix. So if I am able to get cos alpha and sin alpha, I should be good to go, right? Now we are considering vectors because vectors have a way for us to produce sine and cos if we can combine with other vectors. Dot products and cross products gives us the sines and cos values with respect to the angle between them, right? So we are going to deal with that. Now in order to get my alpha, so let's go with this. First thing, this vector is in some plane which is unknown to us. Let's bring it to some known plane. So I am going to take a projection of u onto my yz plane. So projection of u. So for me, u was a comma b comma c, right? Now what I have to do is I am keeping the y and z of it same, but the x as 0. So my u dash should be 0 comma b comma c. So I'm just projecting it, right? Now the magnitude of this is changed. U dash is no more a unit vector for us because it's just a projection. So to get you an idea, put some light from this direction. Assume your yz plane is a screen, and the shadow that this vector u creates on this yz screen is the projection u dash vector, right? Now the angle that u dash makes with this unit vector along z-axis, that is uz, whose value is 0, 0, 1, the unit vector along z-axis, the value of the z-axis is 0, 0, 1. The angle that this u dash makes with uz is same as that of the angle that u makes with the plane xz alpha, right? So now, since the angle is same, and I know my vectors 0 comma b comma c, and I know my vector 0 comma 0 comma 1, and it is the angle between them is alpha, I am going to perform cross products and dot products between them to get my cos alpha and sin alpha. So how to do that? Now we know that if I apply dot product, so this is 0 comma b comma c. If I apply my dot product, then I have magnitude of u dash into magnitude of z, so magnitude of these two vectors into the cos of angle between them. So this formula gives us the cos alpha. Now if I want, I don't know what is my cos alpha, that is what I am intending to find. So if I take cos alpha towards the left hand side, then what I get is u dash dot u z divided by the magnitudes of these two vectors. Now the dot product between these two, so the dot product between this vector and this vector can be given as 0 into 0, the x term is 0, plus b into 0, so that is 0, plus the c into this 1, that is c. So the dot product that I get is c. And then we know that uz is a unit vector, so because of that the magnitude of uz will be 1. Now what would be magnitude of u dash? So the magnitude of u dash will be 0 square, square root of 0 square plus b square plus c square. So I have just not written 0 square here. So the magnitude of u dash is square root of b square plus c square. You have to note b and c is not unknown to me. I know what is my b and c. So b is y2 minus y1 divided by magnitude of v, and c is z2 minus z1 divided by magnitude of v. So let us say the magnitude, let us represent it with the alphabet d. So let us call this as d. So it is d into 1, so that is d. So the cos alpha term is equal to c by t. I know what is my c, I know what is my b and c, so which gives us d. So cos alpha now is represented in terms of known values for me, right? So now that I know my cos alpha, let us see what is my sin alpha. To see my sin alpha, we'll have to perform cross product between these two vectors u dash and uz, 0 comma b comma c. Now the cross product between these two vectors could be given as magnitude of u dash into magnitude of uz into sin alpha, sine of the angle between them, into the unit vector which is perpendicular to these two vectors. So the unit vector which is perpendicular to these two vectors is unit vector along z-axis, that is ux. So ux is the unit vector that we have which is perpendicular to these two vectors. So if I am interested to know my sin alpha, so if I bring it towards my left hand side, I would get this. Now let us see what is our cross product using the Cartesian form. So using the Cartesian form, I would have ux, uy, uz, and then I have my 0 into b into c, that is my u dash, and my uz is 0 into 0 into 1. So what do I have what do I have as my cross product? So I would get ux into b minus c into 0 is 0 minus uy into 0 into 1 is 0 minus c into 0 is 0 plus uz into 0 into 0 is 0 minus b into 0 is 0, so these two terms become 0. So what I get is b into ux. b into ux. So I substitute my b into ux here, divided by, I have ux into, as we discussed earlier, u dash magnitude is d and the magnitude of uz is 1, so these two gets cancelled. What I'll have for my sine alpha is value b by d. So this. Now b by d, b is also not unknown to me, so b is y2 minus y1 divided by magnitude of our actual vector v divided by square root of b square plus c square is what we have as my sine alpha. Now I know my sine alpha and cos alpha. I'll have to rotate the u around x-axis, so what I'll have is the rotation around x-axis matrix is 1 0 0 0 and then 0 cos alpha minus sine alpha and then 0 0 sine alpha, then cos alpha 0, and I would have 0 0 0 1. So the cos alpha for me that we saw earlier is c by d. C by d minus sine alpha is minus b by d, and sine alpha is b by d and cos alpha is c by d. So if I take this matrix and if I multiply apply this matrix on this vector u, that is a b c, then what I get would be u double dash, which will be lying on exit plane. Now, since we have brought down this u onto exit plane, u dash has a along its x-axis. You did not change its x, but the y got 0 because it's on xz plane, and the d is the z-axis. So the magnitude of the u dash is what? Since it's also the projection, magnitude of u dash is, this is also projection, but it is rotated. It is not exactly projection, it's rotated. The magnitude of this rotated vector on xz plane, the z-axis value of this vector is same as the magnitude of its projection that we had taken along yz plane. That is the magnitude of u dash. So I have my u double dash as a comma 0 comma d, and then I have my vector 0 comma 0 comma 1, which is unit vector along z-axis. Now I know, let us say that the angle between them is called as beta. I'll have to find out cos beta and sin beta, just like the earlier how we found out using dot products and cross product between u double dash and uz. Now if I apply dot product between u double dash and uz, then the cos alpha can be represented like this, where we know that this is vector, this is still a unit vector and it is rotated. So u is just rotated, we did not take it as a projection, it's a rotated. Since it is rotated, the dimension or magnitude of that did not change, so u double dash mod will be 1 and uz magnitude is also 1, so the denominator will be 1. Now if we look at the dot product, I would have 0 into a plus 0 into 0 plus 1 into d, which gives the dot product as d. So cos beta that we would get would be d. Similarly, if we take the cross product, what we get would be, so sin beta will be equal to u double dash into uz divided by uy. So these three terms will get as denominators here. Now we know this is 1 and this is 1. So if we apply cross product between them, then we have A 0 and D 0 0 1. So ux terms become 0 because we have 0 over here for uy. Uy term becomes uy into a minus 0, right? And uz term becomes 0 because we have 0 here. A into 0 minus 0 into 0. So what we would have as u double dash cross uz will be a into uy. So sorry, minus a into ui. Oh yeah, since we will, so there will be a negative sign here while we compute the cross product. So we get minus uy into a. So we would have sine beta is equal to uy into minus a divided by uy into the magnitude of these two vectors are 1 and 1. So these uy gets cancelled. Sine beta that we would have will be minus a. So we know that cos beta is d and sine beta is minus a. If I'll have to rotate it around y-axis. Now y-axis rotation matrix is, this is cos beta and this is sine beta. This will be minus sine beta and this will be cos beta. So if I replace these values, I would get this matrix. So D minus A and D are known terms to me. So if I apply this matrix over vector u double dash, what I will get is the vector which will be aligned with z-axis. So now that we have our vector along z-axis, so u is brought onto z-axis now. Now I'll have to rotate my object around z-axis. So the rotation is performed using z-axis rotation matrix. So we've seen that in the 3D transformations video, all these rotation matrix. So theta will be the angle of rotation that user would like to rotate, how much ever he wants to rotate the object around the reference axis, that would be the theta. So plugging in that theta value, whatever we get, so theta here would be a known term for us, which would be anticipated amount of rotation that user needs around the reference axis, right? So we apply that, and the steps that we would do is we apply translation to bring it onto origin. Then we apply rotation around x-axis, which will bring this object onto this axis onto xz plane, and then we rotate it around y-axis, which will bring the axis on z-axis. So this is basically from this step to this step, we'll have to perform Rx of alpha first and then Ry of beta. Once I perform, it gets aligned to z-axis, and then I apply my Rz of theta rotation matrix that would rotate my object around z-axis. After that, I'll have to bring this axis back to its original orientation, one step back. So we'll have to bring it back by undoing our y-axis rotation. So the first step that I would do here would be y inverse or y inverse of beta, and then I'll have to perform a rotation to take it back from xz plane to its original orientation. That is, we'll have to inverse our alpha rotation around x-axis, that is our x of alpha inverse, our x of alpha inverse. Now this is our z of theta. This is t for us, and after we undo it and get it back to its original orientation, we'll have to move it back to its original position. That we do by inversing this translation. So this step will be t inverse. So we perform translation, that is t, and then we perform rx of alpha, and then we perform ry of beta, and then we perform rz of theta, and then we perform inverse of ry of beta, and then we perform inverse of rx of alpha, and then we perform inverse of translation, that is t inverse. The resulted matrix, if we multiply with any object, that would rotate the object around the arbitrary axis that we have considered here. So this, guys, are the steps involved to rotate any object around an arbitrary axis, whichever might that axis be, if it's not parallel to any of the principal axes. So moving forward, let's see our 3D reflection. So 3D reflection is similar to that of 2D reflection that we have seen. So over here we reflected in 2D, we reflect an object with respect to an axis like this, but in 3D we reflect the object with respect to a plane. Now if we consider xy plane as our reference, if we reflect this, this xy plane acts as a mirror, so whatever we have here should get inverted, right? So the z-axis gets inverted here. So every let us say if an object is here with respect to z, then this object will go here with respect to the reflected axis. So to do that, we will just have to invert our z-axis values, keeping our x and y same. So this matrix would invert the object by xy plane. So on this notion, we can build our own reflection matrix based on whichever plane we want to reflect it with respect to. Moving forward with respect to shear. So shear we have seen in 2D shear, when we have an object, in 2D we shear it with respect to some reference axis. If we shear it with respect to y is equal to 0, then we will get the result as this. Whichever object is lying at line y is equal to 0 is unmoved, but after that, depending on how far it is, which level of y is in the object, so it moves away from the y-axis by so much. So since this layer here is closer to y is equal to 0 line, it has moved a little, and this layer here in the object is quite far away from y is equal to 0 reference line. It has moved a little away, a little more compared to this. So it has moved by maximum extent with respect to this object, because it is the farthest layer in the object, right? So that's our 2D shear. So if we move with respect to this line, this object, then we would get our object would move something like this with respect to this line. So the same concept we extend it to 3D. Now here when we shear it with respect to z is equal to 0 plane, then whichever layer in the object is on z is equal to 0 plane here, which is on my xy plane, will remain in the same position. Whichever layer is far away from this plane, E will move away, in both x and y directions, since it's 3D. So this is moved away more. Somewhere in between, if you take, this is moved relatively by half as that of the front plane, right? So this is the shear matrix that we have. If you look at, we have shear factor with respect to x-axis as well as y-axis. Over there we would have had shear factor with respect to x-axis and y-axis in 2D, depending on with respect to which axis or which reference line we are shearing with. Here, since our reference is z-axis, we have taken zref over here as the reference axis. So that's it about rotation in general rotation, 3D rotations and 3D reflection and 3D shear, guys. Hope you have understood, and thank you, guys.